Hey everyone, in this video we're going to go through the solutions to the General Maths, Recursion and Financial Modelling Chapter 7 test, so Chapter 7 from the Cambridge textbook. I'll try to go through as quickly as possible just so we, the video is not too long. Alright, so question 1. A sequence of numbers is generated by the recurrence relation shown below. So 2, 0 is our starting value, so we start at 5. And Tn plus 1 is negative Tn. So this basically means we're doing negative 1 times Tn. All right, so the value of T2. So we've got T0 equals 5. T1, we're just multiplying that by a negative. So it's going to be negative 5. And then to T2, we're multiplying negative 5 by negative 1. So we're going to get 5 again. So basically, your pattern is going to be 5, negative 5, 5, negative 5, and so on. So our answer to that one is D. All right, moving along. Use the following information to answer questions 2 and 3. Gus purchases a coffee machine for $15,000. I'm going to highlight in this question because we've got a bit going on. And depreciates its value using the unit cost method. The rate of depreciation is 4 cents per cup of coffee. A recurrence relation that models the year-to-year value, blah, blah, blah. So there's our recurrence relation. And we're going to use that to find the rule of the machine after n years. All right, so we're starting off with $1,500. So I'm going to just do a process of elimination of the options that it can't be. So obviously it's going to be 1,500. And then it's depreciating. So it's got to be minus. So it can't be B. That leaves me with options A and C. And they're the sort of things that you could start thinking about during reading time. All right, so all of that I can do during reading time. I can't write, but I can do that sort of thinking in reading time. Now, we've got the value after n years. So we've got two main things that are different here. We've got minus 0.04n and minus 1,314n. Now remember the depreciation is 4 cents per cup. So A actually is what it would be per cup, whereas C is the depreciation for year. All right, so we can see it's per year here, and then the 1,314 is there. So your answer is C. All right, so sometimes it's easier just to do a process of elimination and then actually thinking about, well, what do I have left? So option A is the depreciation if you're looking at per unit, whereas C is the depreciation per year, all right, because it has told us the year-to-year value. The number of cups made by the machine each year is, all right, so we're depreciating by 1,314 and each cup is depreciating by 4 cents. So we're going to divide that by, and that should be in dollars too. Not that I need to write the dollars there, but just to make it make sense to you. All right, so it's 1314 divided by 0.0. Oh, whoops. 0.0. Sorry, I can't read the 0.4. There we go. All right, so 32850. So that's how many cups are made each year. All right, so quite a few. Just before we move on to question 4, you're probably thinking, well, why is it doing per year when it's a unit cost? All right, so if you start thinking about just doing a recurrence relation or a rule using the unit cost, you're going to go very high with your values of n because it's just 4 cents each time. They're kind of, obviously you wouldn't be selling exactly 32,850, but you'd probably, if you were owning a coffee shop and depreciating this coffee machine, that would be approximately what it, how many you would make in a year, which would then give us a depreciation of 1,314. All right, moving on to question 4. So the value of a computer purchased for $6,000 is depreciated by a flat rate of 8% per annum. So the main difference between a flat rate depreciation and a unit cost is flat rate is the same amount each year, whereas unit cost is per unit of use. So the previous question, it was per unit of coffee, and flat rate is 8% per year. All right, which one of the following recurrence relation models, blah, blah, blah. All right, so when I'm looking at questions like this, process of elimination. So we're starting with $6,000. All right, so I can't eliminate any options there. Let's have a look at our recurrence relation. They're all written with the VN+1, which is good. And we're doing depreciation, and it's an example of linear decay. So C, D, and E are all examples of geometric decay. So flat rate is a linear decay, and that is on your summary sheets. So it only can be A or B. All right, so we're doing 8%. I know that 10% of 6,000 is 600, so I could automatically just say it's A, but let's do 8% of 6,000, and I know it's going to be 480, so 0.0, actually, let's clear that. All right, so we take the 8%, divide it by 100 to turn it into a decimal. All right, that's what I was about to write before, but I just wanted to show you how to get that. And then we multiply that by 6,000. All right, so there's your 480. Answer is A. All right, for taxation purposes, Audrey depreciates the value of her $3,000 computer over a 4-year period. At the end of the 4 years, the value of the computer is $600. If Audrey uses flat rate depreciation, so remember that's an example of linear decay, the depreciation rate per annum is. So she started off with $3,000, or the computer's worth $3,000, and it's now worth $600. So the difference is $2,400. So it's gone down by $2,400 in 4 years. Now flat rate depreciation is per annum, so let's just divide that by 4, and that's going to give us $600. So basically it's $600 per year. All right, with flat rate depreciation is a percentage of the original amount. So remember back here we took 8% of the 6,000, so it's 8% of your original amount. We don't know what percentage we're multiplying by 3,000 by to get 600, but to work that out, we just take 600 over 3,000 and multiply it by 100, and that will give us our interest. Not our interest, our, oh my gosh, I can't think. Let me type this in while I think. Our depreciation rate, that's the word I was looking for, times 100, or rate of depreciation. All right, so 20%. That question there, probably can't do any, I probably couldn't do any elimination. If I had no idea as to how to do it. Probably a bit silly, these options, because we've got 600 here and then we're repeating another 600. So you could accidentally get that 20% in that, well, you could incorrectly get the right answer, which is fine. But yeah, just the amount per year. So 600 is how much it's depreciating by each year. 3,000 is the starting amount, and then this times 100 is turning it into a percentage. All right, question 6. The rule for the future value of an asset after end depreciation periods is this. So there's our rule. The method used for depreciating the value of this asset could be. All right, so this part here tells me that it's linear. Okay, we don't have a common ratio. All right, it's going down by the same amount each time. So it's starting off with $4,000 and it's going down by $20 per year or $20 per unit. Now, it's not reducing balance, because reducing balance is an example of geometric decay. It could be flat rate. It could be unit cost. All right, so let's keep going. Either flat rate or reducing balance, so it can't be reducing balance. Either flat rate or unit cost, so option E. All right, so a bit tricky because it can be B and C, but it does say only, but it can be either flat rate or unit cost. So this rule is an example of linear decay. All right, so we've got, yeah, can be either flat rate or unit cost. Jeff purchased a computer for $4,500. He will depreciate the value of his computer by a flat rate of 10% of the purchase price per annum, a recurrence relation that Jeff can use. Okay, so we want to start off with 4,500, which they all do. So let's eliminate anything that is not a flat rate. So C, D, and E are all examples of reducing balance depreciation. And it is depreciation, so we've got to do the minus. All right, if it was plus, it would be going up in value. The minus means it's going down in value. So that should be a gimme mark. All right, that's a very, very easy question to do. All right, probably understanding the difference between flat rate and reducing balance though. So just make sure when you see flat rate, you go to those notes in your book if you're unsure. And remember, during reading time, you can read your notes. Okay, so if you during reading time come across the word flat rate and you're a bit unsure, you can read your notes. Mo invested $10,000 into an account that earns interest compounding fortnightly. The balance in dollars after n fortnights can be modeled by the recurrence relation shown below. All right, so now we're looking at effective annual interest rate for Mo's investment. All right, so there's a bit we have to take into consideration here. We've got a recurrence relation. The initial value doesn't really matter. All we need is the interest rate now and the compounding period. So it's compounding fortnightly. And I just want this value here, our, oh my gosh, what is it called? Our common ratio. So remember, that is found by R equals 1 plus our interest rate over 100 times P or N, depending on, I think in your notes it's N, but I'm going to use P for compounding periods. All right, so R is that common ratio, lowercase r, which is what we're solving for, and then P is how many compounding periods per year. So it's fortnightly, so there's 26 compounding periods in a year. Now, if we had to solve this by hand, we're going to subtract 1 from both sides, blah, blah, blah. All right, I'm not going to do it here. We're going to just put it straight into the calculator using solve. All right, so whoops. All right, so my computer doesn't like it when I have the screen flipped over. It always takes, probably get it done a lot quicker if I did this by hand, but anyway. 1 plus, all right, putting our fraction in. So instead of trying to search for R, I'm just going to do that. You can just do 100 times 26, but if you know that is 2,600, you could do that too. Doesn't matter. Probably safer just to type it in as it is in case you miss out on a 0. All right, didn't have to do comma X, but we are. All right, so R is equal to 2.6. So it's 2 decimal places, so that's why it's 2.60. Oh, actually, hold on. I forgot. The question's asking for the effective interest rate. So this is your nominal interest rate, what you get from your calculator. So we do have to go one step further. Oh, tricky, nearly got me. Interest conversion, convert to effective. All right, so N is the number of compounding periods per year, so 26 fortnights in a year. And your nominal interest rate is 2.6. All right, that's going to give us the effective. All right, there we go, 2.63. Nearly didn't get it. All right, question 9. Which one of the following recurrence relations generates a sequence in which the values grow geometrically? So we want it to increase, so it means it's got to be greater than 1. Right, if it's decreasing, it's less than 1. And geometric just means it has a common ratio. So I can get, so this is 0.8, which is less than 1. So it's not going to be A. 1.2 is, so your answer is going to be B. 0.8 again. And then D and E, you can see this one's not growing geometrically because we've got a value of 1 and it's adding 100 each time. And then this 1.2 here, but we've got a combination of both geometric and arithmetic. All right, so your only possible answer is B. All right, question 10. Sammy purchases a boat for, oh God, expensive boat, Sammy. $72,000. The value of the boat is depreciated each year by 10% using the reducing balance. So reducing balance is geometric. All right, so you geometric decay. So just make sure you're aware of that's different to flat rate and unit cost depreciation. In the third year, the boat will depreciate in value by 10% of. All right, so let's actually have a look at this as a recurrence relation. So V0 is our initial value. And then when we write it as a recurrence relation, we got Vn plus 1. And it's depreciating yearly, but my R value is going to be 1 minus our interest rate over 100 times our Vn. So that's, if you did that on the calculator, it's going to be 0.9 Vn. Now, think of, if you ever get confused with this common ratio, think of your phone battery. All right, something that you look at probably at least 2,000 times a day. So full battery, 100%. Right, so it's one whole battery. When you lose battery, so let's say you're on it, you looked a bit at TikTok in the morning before school, you lost 10% battery. So you got 90% left. So this 0.9 is the same as 90%. You've lost 10% by watching TikTok and you're now at 0.9. Okay, so that's why it's less than 1. All right, it's going down. So depreciation is going down. All right, so V1, we just do 0.9 times our previous value, which is 72,000. All right, so we get 64800. All right, we want the third year. So that's our first year. This is our second year. So we'll do that again. Times 0.9. So 58320. 58320. So V3, you're going to take 10% of this amount. Oh, well, sorry, it's going to depreciate by 10% of that amount. So 0.9 times 58320. It's not asking you what it is. It's depreciating this value by 10%. So that is option C. All right, question 11. The value of an investment in dollars after n years can be modeled by the recurrence relation shown below. All right, so this is our initial investment, and we don't know what R is. I guess probably have to work that out. This investment earns compound interest at the rate of 5% per annum, compounding quarterly. What is the value of R? Now, this is an investment, so R has to be greater than 1. All right, so greater than 1, so it can't be A. All right, we can knock that off. And your option, you're going to have 4 options this year. So the exams have changed, so you have it out of 4 options. So instead of being now, I only have 4 options left. If this was on your exam, you'd have 3 options left. All right, another thing you can think about is you've got 5% per quarter. So you can kind of see, well, I could probably get rid of these 5s, all right, because it's not 5% per annum. Sorry, it is 5% per annum, But that percentage, when you do your R value, is going to change. So it's not going to be B and it's not going to be D. So your options are going to be either C or E. All right, so if you had to guess, you got a 50% chance of guessing. But let's have a look at what it is actually. So R is calculated by doing 1 minus, so it's, no it's not, it's plus when you're doing an investment. Sorry, I was getting a little bit confused. 1 plus your annual interest rate over 100 times the number of compounding periods. Now, in your notes, you may have an N here. All right, same thing, guys, but I'm just going to use P because I prefer P now. All right, 1 plus your annual interest rate over 100 times 4. So we'll just do that on the calc. So 1 plus, and then we go shift, divide to get our fraction up. 5 over, and we all know that 100 times 4 is 400. And there we go, 1.0125. Okay. All right, moving right along. So question 12, we got a graph. The graph could represent the value of. All right, so looking at this, I can see it's linear, pretty linear. I think if it was geometric, it would clearly be non-linear. All right, so let's just look at our options. The balance of a savings account earning simple interest. A possibility. Let's just put a tick. Let's have a look at the other options. An asset as it depreciates. Well, if it was depreciating, it would go down in value. No, thank you. A perpetuity earning compound interest. Now, a perpetuity doesn't actually change in value. So you may not have done perpetuities yet. And you're like, oh, how am I supposed to answer this? So a perpetuity, yes, it's not an example of a perpetuity. So hopefully you were okay with that. An annuity from which equal regular payments are withdrawn. So an annuity and a perpetuity is a type of annuity. An annuity also goes down in value, but your payments, so you earn interest and then you also receive payments. So it's not actually an example of an annuity. It's a bit hard to explain and draw a graph of, because an annuity is an investment that you earn interest on, but you also get payments from. And reducing balance is an example of geometric, so it can't be E. So first option, which is A, which is super duper great, because if we're in a rush, we could just circle A and move right along. But during reading time, you'd probably read all those other options. All right, question 13. Bibi, or is it bye-bye? I think it's Bibi. Took out a loan of $3,000 from her bank. Interest for this loan is compounded monthly. In the first year, Bibi made no repayments. The effective rate of interest for the first year was 4.18. The balance of Bibi's loan after 1 year. Oh, so much going on, Bibi. All right. The first thing I've noticed is we've been given the effective interest rate. We need to work off the nominal interest rate. So we're going to do convert to nom first to get our rate of interest per year. So on our calc, we go to interactive financial and then interest conversion, and then we want to convert nominal. All right, and it, remember, is the number of compounding periods a year. So we've got monthly, so it's going to be 12. And then the effective interest rate is 4.18. Now remember, your effective interest rate is always higher than your nominal, so I should get something less than 4.18 here. And it's 4.102. Now, see how I've rounded there? I'm going to, whenever I need to use this, I'm going to highlight that whole thing. All right, so it's best not to do any rounding on your calculator. Just highlight and drag. All right, so we've got $3,000. All right, I think we can do this in Financial Solver. So I haven't done these questions. Well, I have probably done them before, but oh, I can just clear page. Sorry, guys. All right. So we're doing, only 1 year, so it's monthly. So we've got to do 12. The interest rate, oh, this is where I'm going to go back here. Let's highlight this, edit, where are you? Copy, and then we can go back to financial. Pretty sure, guys, I typed in 12 there and didn't want to stay. All right, let's paste. Now, your principal value, if you're taking out a loan, it's going to be positive. It's money coming to you. That's all in your notes. All right, made no repayment, so it's going to be 0. So it's kind of like an interest-only loan. The future value is what we're looking for, and the compounding periods. So remember, these last two are always the same. Come on, future value. So $3,125.40. Right, so the balance in the account. All right, moving right along. Question 14. Jen invests $10,000 at an interest rate of 5.5% per annum, compounding annually. After how many years will her investment first be more than double its original value? So it's compounding, clear giveaway. We're just going to type this into the calc. So edit, clear the page. All right, so after how many years? So that's what we got to work out. So I'm going to leave N blank. Our annual interest rate is 5.5. So remember, we don't have to calculate that unless the word effective has been used anywhere. We just assume it's the nominal interest rate. Now, if you're investing money, it's going to the bank. So that's going to be negative 10,000. We're not making any payments. And the future value, we want it to double. So double 10,000 is 20,000, and it can be positive because it's effectively going to be money coming back to you. And it's just compounding once a year. All right, so work out N. Now, have a look here. If we were to do 12, we're not going to get double. So if I just get rid of all this and do 12, our future value, we're not going to get over 20,000. So we do have to go up to 13, and then we're over 20. So it's first be more than double. So it's going to be 13. All right, Manu invests $3,000 in an account that pays interest compounding monthly. The balance of his investment after N months can be determined using this recurrence relation. All right, so that is pretty much the only important part there that it's going to help us with our interest rate. The total interest earned by Manu's investment after the first 5 months is closest to. All right, so I don't have enough information that they've given me to just put the interest rate straight in. So I do need to use this value of R. All right, so we're doing a compound interest investment. So your R value is calculated using this formula, which is on your formula sheet. Remember, you might have an N there instead of P. So that's 1.0048. Our interest rate is what we've got to work out, and the compounding periods is 12. All right, so get my calc, go back to main. All right, so we're just going to solve for R, so 1.0048. Now, there is a quicker way of doing this, and you're probably thinking, why am I not doing that? That's because for the majority of you, you need to get used to using this formula here. So R is what we're solving for. I'm just going to put X on the calculator. And also, you could get a show that question. So if it was a show that question, you need to be able to understand what's actually going on here. So your interest rate, oh, why didn't I take notice? 5.76. All right, so that is your interest rate. Now we can use Financial Solver. All right, and we're going to clear everything from there. So we've got 5 months, so N is going to be 5. The interest rate is 5.76. The principal value, so it is an investment, so we've got to put it in as negative 3,000. Payments, not making any payments. And I can tell because in our recurrence relation, there's no minus or plus I should say. Our future value is what we're going to look for, and it's compounding monthly, so 12 and 12. All right, so the future value is 3,072.69. So that's after 5 months. Now we want to work out the total interest. So if you've put $3,000 in, we just take away that 3,000, and whatever is left over is how much interest we've got. So it's a bit easy to do. So 72.69. All right, so a bit of a multi-step question, and also needing to work out, well, what do I need? So starting with your financial solver, you should be putting things in and realize, well, I'm calculating the future value, but I also don't have the interest rate. And when you're calculating the interest rate and you're being given the common ratio or capital R, then you can just use that formula that I've got here. All right, last multiple choice question. The graph below shows the value in dollars of a compound interest investment after n compounding periods. The coordinates of the point where n equals 2 are, all right, so we know something between 580 and 780. Can we eliminate any of them? No, unfortunately. Oh, that's a bit annoying, isn't it? And you might also think, oh, can I look here? Does it match up to anything? That's what you could do if you're a little bit desperate and you didn't know how to answer it. All right, we do actually have enough information here to do a recurrence relation. So let's start off with V0, our starting value, which is 500. All right, tells us that. So when it's 0, it's 500. Oh, my dog's sleeping and making weird noises in her sleep. All right, so R times Vn. Now we do have to work out what the R value is. So we can use probably V1 and V0, the two easiest values. So V1 is 580. So substituting this into this part of our recurrence relation. So I've got 580 is equal to R. So R is going to be 1 plus R over 100. Doesn't really matter doesn't tell us how many compounding periods, so we can just leave it like that because it doesn't actually matter. Times Vn. So Vn is the previous value, which was 500. All right, so I can solve for R just like I did before. All right, so we go to solve. 580 equals 1 plus, oh no, we didn't do R this, sorry, didn't do R this way before, did we? X over 100 times 500. Oh, what did I do wrong? Oh gosh, what's going on here? Why is there an equal sign? Alright, and I need to put, God, you can tell I'm tired. It's what, nearly 5:30 in the afternoon, and I'm not functioning too well. Come on. Can you put a bracket there for me? Thank you. Alright, so R is equal to, no, hold on, what did I do wrong? Alright, I'm just going to pause for 1 sec just to see where I've gone. Oh, actually, we probably could be right. So that's 16%. What are we doing? compounding. Okay, well 16% seems too high, but I'm going to keep going. All right, so our R value is 16. So if I'm doing V2, is going to be equal to R times my previous value, which was 580. All right, so we've got 1 plus 16 over 100 times 580. Oops, wrong button. So 1 plus 16 over 100, close bracket, times 580. So 672.80. All right, let me just talk about this question a little bit more because it's quite complicated. So what I've done is I thought, well, let's have a look at the information we've got and create a recurrence relation. So using a recurrence relation, or you could also use a rule, will actually help you solve. So I decided on recurrence relation. I don't know, it's the first thing that came to my head. So we start off with V0. We also know V1. So we can say, well, I know these values. So in the past, you've had to probably calculate V1 given the value of R. This time we've been given V1 and we have to calculate our interest rate. All right? It doesn't tell us anywhere what our interest rate is. So I use the relationship between V0, which is 500, and V1, which is 580. All right, so V1, let me just write this. So this is V1 and this is V0. That gives me an R value of 16, which is 16%. Now, the reason I was a bit suspicious of that, because 16% is a very high interest rate, whether it's an investment or a loan, very high. So this one here, it is an investment. I'd love to have an investment that earns 16%. But anyway, so now that I've got that R value, I can just substitute it in. All right, so into our recurrence relation. So we've got, let me write it in a different value. We've got V2 here, and this is the previous value, V1. So $672.80. All right, so now we're getting to some short answer questions, or extended response, I should say. Rosalind invested some money in a savings account that earns interest compounding annually. So it's an investment. The interest is calculated and paid at the end of each year. Let VN be the amount of money in Rosalind's savings account in dollars after N years. The recursive calculations below show the amount of money in Rosalind's savings account after 1 year. So we've got V0, V1, V2. How much money did Rosalind initially invest? So the way your exams work, your very first few questions on each module are pretty easy. So I'm guessing this is probably one of the first questions in the financial module, because easy, 5,000. We don't overcomplicate it. Always think, all right, they're going to be easy questions to start off with. So $5,000. How much interest in total did she earn by the end of the second year? So the end of the second year, she got this amount. So 5,512.50. So we're just going to do the difference. So we're left with $512.50. Another easy mark. So if you have a look at assessors, and these questions are all past exam questions, if you have a look at assessors reports, you should get like around 90% or even higher for those two questions. All right, let VN be the amount of money in Rosalind's savings account in dollars after N years. Write down a recurrence relation that can be used to model the amount of money in Rosalind's savings account. So above, they've just given us the application of the recurrence relation. They actually haven't given us the recurrence relation. Now, a recurrence relation has two things. You've always got to state the initial value. So V0 equals 5,000. And then we've got Vn plus 1 is equal to, now it's a compounding interest investment. So it's going to be 1 plus, does it tell us what the interest rate is? All right, so we can work that out. Oh, there it is. So this 1.05, and because it's compounding annually, that's not going to change. So I'm just going to get rid of that because it's already told us. And then it's going to be times the previous value. All right, another kind of straightforward mark. If you recognize that that was your common ratio, all right, just using it already, and then in part C, we're writing the recurrence relation. Rosalind plans to use her savings to pay for a holiday. Oh, isn't that great? Oh, $6,000. All right, what minimum annual percentage interest rate would have been required for Rosalind to have saved this $6,000 after 2 years? Rosalind plans to use her savings to pay for a holiday. The holiday will cost $6,000. What minimal annual percentage interest rate would have been required for Rosalind to have this saved? All right, so she's got $5,000. We're going to assume that there's a different, all right, so we're going to use a different interest rate, and she wants to have it for 2 years. All right, let's plug this all into the calculator. All right, so let's clear. All right, so 2 years, so it's just 2 because it's compounding yearly. So we can put the 1 and 1 here. Our interest rate is what we're calculating. All right, the principal value, so she's investing $5,000, so it's got to be negative. She's not going to be making any payments, so we're just going to keep that as 0. And we want the future value to be $6,000. And she's getting that money back, so it can just be positive. All right, so your interest rate is, what is it, to 1 decimal place, so 9.5%. Whoops, we don't want to write in that. All right, moving on to question 18. Richard will join Rosalind on the holiday. He will sell his stereo system to help pay for his holiday. Well, you're probably thinking, what is a stereo system? So you guys now just have these tiny, tiny little speakers. So once upon a time, when I was a little girl, we would have huge stereo systems with huge speakers. And if you walked into someone's house and they had these massive speakers, like the size of a fridge, you'd be like, oh my God, these guys are rich. So obviously, you know, these guys are rich because they've got a stereo system. But now you just pick up like a tiny, like Coke bottle size speaker that probably has the same power as, you know, these fridge size speakers, stereo systems. All right, anyway, getting distracted here. He'll sell his stereo system to help pay for the holiday. The stereo system was originally purchased for, oh, what a rip-off, Richard. Go to GB Hi-Fi and pick up like a $60 speaker. Richard will sell the stereo system at a depreciated value. All right, so obviously he's buying it for $8,500. You're not going to resell it. Mind you, if this was back in like the 80s and he still had it, he'd probably, you know, sell it for a bit more because it's antique. All right, Richard could use a flat rate depreciation. Let SN be the value in dollars of Richard's stereo system n years after it was purchased. This value of the stereo system can be modeled by the recurrence relation below. So here it is initially, and it's going down because it's flat rate. It's the same amount each year, so it's going down by $867 each year. Using this depreciation method, what is the value of the system 4 years after it was purchased? So it starts off with the $8,500 and it's going down by $867 per year. So if it's 4 years, we multiply that by 4. Don't need to put it in brackets. Your calculator can handle it, but you can, you know, I just like it like that, you know. All right, so we go 8,500 minus 867 times 4. $5,032. Calculate the annual percentage flat rate depreciation for this depreciation method. So we're taking that $867 over the original amount and multiplying it by 100 to turn it into a percentage. So 867 divided by 8500, and then we're multiplying that by 100. 10.2%. All right, no rounding. Don't round unless it specifies to. Richard could also use a reducing balance. All right, so remember, reducing balance is an example of geometric decay with an annual depreciation value of 8% or rate of 8%. Using this depreciation method, what is the value of the stereo system 4 years after it was purchased? All right, so we can just do this in, we can do it in Financial Solver. I'm going to show you using the rule. Let's write a rule because we haven't written a rule for any of these. So if I'm writing the rule, Vn is equal to R. So when you're depreciating, it's 1 minus your annual interest rate over 100, and then to the power of n times V0. All right, so that's our rule. So just substituting everything in, 1 minus 8 over 100. We're doing it for 4 years, to the power of 4 times 8,500 was our initial value. All right. 1 minus 8 over 100. Put that to the power of 4 because it's 4 years, and then we multiply that by the original amount. And we're doing it to the nearest cent, so 6,089.34. All right, 4 years after it was purchased, Richard sold his stereo system for 4,500. Assuming a reducing balance depreciation method was used, what is the annual percentage rate of depreciation did this represent? All right, so kind of similar to before. So we did, we were given a percentage, so this 8% up here. This time we've got to calculate a different percentage. So we can still use the same rule. We're just going to be, we know that, so is it 4 years still? Let me just see. Oh my gosh, where are we? After 4 years, so still 4 years. All right, so V4. So this was V4 for that one. Different V4, but it's okay. We're still just doing our calculations. 1 minus some interest rate over 100 to the power of 4 times 8,500, and that is equal to 4,500. All right, so before we knew the interest rate was 8, this time we know the value of the stereo and we're calculating the interest rate. So we can just put all of this, not the V4 part, but all of that into solve on our calculator. So solve. And there are other ways you can do this question. So if you did it slightly different, that's fine. Just make sure you understand all the different methods because some are easier than others, and just because I'm doing this method doesn't mean it's the easier one, it's just the one that first comes to my mind. All right, and that is equal to 4,500. What did I do? All right, need another bracket here. Come on, let me put a bracket in. Thank you. All right, so we've got two values. All right, so it's going to be 14.7%. All right, can't be the other value because that's 185%. Just doesn't make sense, guys. So 14.7%. So it's worth 2 marks. I think what I've written there would get you 1 mark, and then the 14.7%, yeah, you'd get, if you got that answer, you'd get your 2 marks. All right, whew, hard work. I'm exhausted. All right, guys, catch you later.